Hi, in this video, I summarize the solution of a homogeneous linear second-order differential equation with constant coefficients. The form of the equation is like this: ay double prime plus by prime plus cy equals 0, where a, b, and c are constants. It's a homogeneous equation, meaning the other side of the equal sign here is a 0. It's linear because the y double prime, y prime, and y terms all are appearing in a linear term, not any other power. It's second order, meaning the highest derivative of y is a y double prime. And constant coefficients refer to the fact that a, b, and c are constants. The first step in solving this differential equation is to write the characteristic equation of it. And we do so by copying down the numbers a, b, and c, the constants, right, constant coefficients, and make it ar squared plus br plus c, r squared from the y double prime term, or with the y single prime term, and c is just a constant because this is not a derivative at all. So we end up with a quadratic equation in R. And a quadratic equation can be solved. If you can factor it, then factor it, but otherwise you can just solve using quadratic formula. Well, when we solve a quadratic equation, then three things could happen. We could end up with two distinct real roots. That's one possibility. If we use the quadratic formula, then it happens when b squared minus 4ac is a positive number, then we get plus the square root of that and minus the square root of that. The second possibility is if you have just one root. That's how we used to think of it in elementary algebra. Right? But as you learned in either college algebra or pre-calc, it's considered a doubled root. It's considered that two roots are occurring at the same spot. That's called a doubled root some number r. This happens when you solve using the quadratic formula and you end up with b squared minus 4ac equals 0. Then in the quadratic formula you have square root of 0 plus or minus square root of 0. So the two roots occur at the same spot. And then the third possibility is if you end up with a complex number. This happens when b squared minus 4ac is a negative number. And in the quadratic formula, you take square root of b squared minus 4ac, you get an imaginary number in there. Right? Then you have two complex roots, and they are always complex conjugates of one another. One would be a plus some beta I, and the other would be a minus some beta I, and that is because of the plus or minus square root of b squared minus 4ac. Right, so in the complex root, the alpha plus beta I and alpha minus beta I, the alpha is considered the real part of the root, and the beta is considered the imaginary part of the root. Each of these three outcomes or possibilities will lead to a different solution of the differential equation. The prototype is the case of two distinct real roots. You end up with R1 and R2. Then what you do is you put R1 with x and you put the whole thing in the exponents of e to the power. So for the first value R1, you got e to the power R1x. And for the second value of the root R2, you got e to the power R2x. So that's the prototype of how to write the fundamental solutions. These two are the two fundamental solutions, and the general solution to the differential equation would be any linear combination of these two fundamental solutions. You could have any arbitrary constant C1 times the first fundamental solution plus any other or the same arbitrary constant C2 times the second fundamental solution. And that linear combination will be a solution to the original differential equation. So we call this a general solution of that equation. Well, what do we do with if we have a doubled root r? You would say, okay, so we do the same thing. We put r with x in the exponents. And you would be partially correct. We put r with x into the exponents of e, and that would be a fundamental solution. But if we do it again, because it's the same r, we would get just the same solution again, and that doesn't work. So instead, we put an x in front of it. So instead of just e to the rx and another e to the rx, is e to the rx and then x times e to the rx. You will learn that this is a form of what's called variation of parameters. So the two fundamental solutions, because the r repeats, we have to distinguish one of them by multiplying by x. And the general solution, again, is the linear combination of these two fundamental solutions, e to the rx and x times e to the rx. Moving on to the case of complex roots, the two roots are complex conjugates of each other, so we don't care about the plus or the minus here. We only care about the specific value of the real part alpha and the imaginary part beta, just the beta, not the I. The alpha is real, so it looks just like the r here or the r1, r2 up there. We're going to put the alpha together with x and put it in the exponents of e to the power. So we have e to the power alpha x times, well, this beta I here, we won't be putting it in the exponents, but instead we use Euler's formula to turn them into a cosine and a sine. So we end up with two fundamental solutions, e to the alpha x times cosine of beta x, and then e to the alpha x times sine of beta x. So to remember, the alpha is the real part and it goes in the exponents of e to the power. The beta is the imaginary part and it goes into cosine on one solution and sine on the other solution. Then we do the same thing. We take a linear combination of these two fundamental solutions, C1 times the first fundamental solution plus C2 times the second. Or you could factor out the e to the alpha x, and you end up with e to the alpha x on the outside and a linear combination of the cosine and sine on the inside of the factoring. And again, the alpha is the real part of the complex root and the beta is the imaginary part of the complex root. If you want a one-page summary for this whole topic, this is the page. All right, hope that helps. Like, share, and subscribe for more contents. And thanks for watching. Bye.